Okay, let's start our video with the beginning of the universe. So, if everyone talk about the beginning of the universe, it ends up in Big Bang. So, what is Big Bang? And I don't know what is Big Bang, but in detail. But I have a sense that where I am taught, or I mean, popular science culture, that Big Bang is actually the expansion of the universe. But I don't know deep into that. If I ask a simple question, what is Big Bang? What will be the simple answer?
I would say it's not an easy answer because technically Big Bang is very difficult to explain. But naively, it is the beginning of the universe where it all began, and it started out with a big bang, as if there is a bang. So it has to come out at some point where people understood that the universe is expanding, and why is this universe expanding is a different question.
I can interrupt. Like, people start to understand universe is expanding. Is that a simple thing? Like, if we think now, and we are saying, oh, people start to understand universe is expanding. Was that a simple step for the?
I don't think it is a very simple step for anyone to understand Big Bang, because if you want to find your place in this universe, you are on Earth, no matter what you say. You can imagine yourself in some other stars or galaxies, but unfortunately or fortunately, you are on this planet. And all you can do is look up in the sky. That is the best you can do as of now. So you look up in the sky, do you see this universe expanding? Do you see yourself expanding? I would say I don't feel like that. And
so it comes from careful observations and.
Yeah, it is not just careful observation that we need. It's probably insights. We need insights, and we need a very long period as well. Because if you want to model this universe as a whole, it all started maybe since the dawn of light itself. I don't know, but probably we can trace back to the geocentric model. But people assume that the Earth is the center of this universe. See, Earth is the center of this whole universe. Okay, we don't know what this universe is. We don't know how big it is. Even right now, if you ask any cosmologist or an astronomer, they would probably say, "Yeah, this is how much we have observed," and we can't say the universe is infinite. We can't say the universe is finite. All based on observation, we have some content somewhere here and there, and that is all we have.
So I can ask, like, it's all about observation and these kind of things. Does we lack creativity? Like, if anyone from other background other than science, do we say like they are following some rules, they are following some basic things and all? Scientists are not creative. What do you think?
Scientists are very creative. I would say they are the most creative people in several senses.
I mean, where is the creative aspect of? See, if one said that universe is expanding, is based on observation and findings, where is that creative part in that?
Where is the creative part in scientific exploration? I would say it's more or less logic based. We try to explain things based on the logic we have, based on a set of rules, but we are reasonably good at mending the rules. For instance, what can I say? Yeah, let us talk about the geocentric model and how we came from the geocentric model to heliocentric and to the current understanding of the universe. Maybe geocentric is not the right place to start. Maybe people had, even before a geocentric model, before Ptolemy, before everyone else, they might also have their own perspectives of the universe, like Earth was flat. Yeah. Do you see the curvature of the Earth right now? No, we don't. So
I believe it because I taught in school. There is no way I can tell.
When the teacher came up with the globe and told us that the Earth is rotating, I was wondering whether I'll be able to reach home back because it is moving, right? So I was also confused at that point, but later on we were able to understand that that is not how we came to these understanding. Okay? Maybe that is the problem with our education system. We are taught things.
Yeah,
Like
we are taught.
they are
And also
actual.
there is another thing like I want to point out like I taught I've been taught that Earth is round. I never experimented with it.
Yeah.
I never did any experiment to confirm myself Earth is round.
Yeah.
But I still believe because of some people told it. I believe has taken as
Yeah,
granted.
that is the problem with science. Like there is always the secondary narrative that we all get. Even if this conversation led to something, and you are going to tell someone else about this conversation, and someone else is going to interrupt this conversation in several ways. So, unless and until you convince yourself from first principles, whatever your first principles are, it's very difficult to make an understanding of this universe. So I think we should begin with the geocentric model.
Yeah.
So when we look up in the sky, we see stars obviously, and we see sun, moon, clouds, everything else. So do you see a pattern? Do you see, I'm asking you a question, do you see a pattern, any pattern?
Yeah. I can see the pattern. Like sun is rising
Yeah.
in the air.
So we see, so some events are periodic, or some events happens regularly. For example, sun rising in the east, going to the west.
And phases of moon is changing.
Yeah, phases of moon. That's a very good example. So it tends to have a period. So there was this short story which was taught in English class. I don't remember the title, but it is about a slave. So slave was somewhere tied in the outskirts of the village, and he wanted to figure out how much time he's been there. So in a general sense, how can he have a understanding of the time? So he started observing the sun, and sun comes up every day. So maybe he has an understanding of what a day is. But how do you understand 1 year? Like why the number 365 or 365 point whatever people call it? I don't know. Do you know any idea? Do you have an idea?
So I have an idea. Like it's not an idea. I've been told or I've been read in books. There are constellations. Constellations are star patterns in the sky, which is so there is a pattern we can create by the stars around in the sky. So these constellations doesn't change the shape because they are the distant stars. It make up with the distant stars.
Yeah, but this is the problem. We have been taught so much. There is this information overload with us, and that makes us think from very basics. You don't know whether the stars are fixed. You are not, very accurate in mapping these stars because the person I narrated is a slave. Maybe that is a politically incorrect term to refer to right now, but nevertheless, let us assume that he is somewhere in the woods. Maybe that is Mowgli. I don't know. But the point is that he is simply observing. He is not making any rigorous effort to map all these stars and constellations. We know these things right now. But if you look at the sun, can you say 1 year has passed?
Yeah, probably. Because if I say there is a shifting.
Yes, exactly. So there is this shift,
Slight shift
in the position of sunrise throughout the year, and it changes.
But probably the simple answer would be like if he is tied up in the woods, he can that also linked to the slight shift of the sun. He can observe the climate change.
Yeah, climate change is one thing. It's not climate change. Probably you are referring to the weather. So if you look at the sun, it tends to change its position. We call it Uttarayanam and Dakshinayanam in Indian context.
Summer solstice and winter solstice.
Yes. So that allows you to have a notion of an year. Okay. And in the year, then if you make more and more rigorous observations, you still find that your patterns will emerge, then the constellations will emerge, and then we see some periodicity. Now, can you see any constellations right now? No, it's sun. So it is when it is sunny, we can't see anything more than the sun. So it's probably at the night. But if you don't understand how the sun is going around, we probably will not guess sun is right now in this particular constellation. Now it is in the Cancer constellation currently. So that understanding takes time unless someone teaches us that. Um, but naturally there was no one to teach, and people have to figure out all these by themselves. So if the earth is at the center of the universe, okay, I'm referring to the whole universe, and I'm looking up and I see everything going from east to west, okay, so what would you say? Earth is at the center, everything goes around. There is nothing wrong
Yeah,
with
there is
that.
nothing wrong because
Yeah,
we can
that
see
is,
we can believe what we see.
yeah. So the next question is, how do you think we transited from the geocentric model to the heliocentric model?
I think that takes a careful observation. People try to map different things on what they believe. So their belief is now is a geocentric model, and they map different planets and their movements, and they find it difficult to map if Earth is the center of the universe. That's what I thought. I don't know much about it.
Yeah, you're partially right. Not maybe you're completely right. People started looking at particular planets, and there was this inherent belief that everything goes around in circular
Perfect
orbit.
circle. Yeah, I
Yeah,
forgot it.
perfect circles is one thing.
Because heavenly things are
Yeah.
something very heavenly for
Yes.
them.
Yes, we cannot associate our own local motion with them. People have to imagine they are godly things or heavenly things, upon which we don't have any control. And they tend to move in very precise circular orbit. And then there are planets, they're also in the sky, but their position changes, on a regular basis. Maybe not continuously to our own eyes. But if you are careful enough, if you watch, some planets for a few hours, you can see it drifting through the night sky. But the problem is, if that is the picture that you want, and you are very adamant about the circular orbits and everything,
We need epicycles, right?
we need epicycles. Because the Mercury's orbit, Mercury is the part of all paradigm shift, I should say. So if you look at the Mercury's orbit, it tends to show what kind of motion is that? It goes from left to right and then from right to left.
Oh,
It's called
kind
a
of.
retrograde
Yeah,
motion.
yeah.
So why is Mercury doing that? Maybe Mercury is the evil thing. Maybe it is not too divine to follow a circular orbit. Uh, maybe,
I want to
yeah,
make a spoiler because Mercury is one of the planets. It's very famous for gravity, and Mercury is
yeah. That is what I said. It is the epicenter for
all
most
the
of the paradigm
yeah.
shifts. So if you look at Mercury, um, right now we know how Mercury is moving, but what we tend to see is that it goes from left to right and right to left. Okay, that is kind of a retrograde motion. That is more like a racetrack. So if you are in a stadium, you see the races. Okay, whether it is a um, you know car car race or any other kind of race, you see the cars going from left to right and then from right to
Yeah, it's
left, because it
following.
is going around something else, not us. If it is going around us, we will always see them go to left to right or right to left. Once we fix that, it is not going to change. But with the sun and the Mercury now picture, Mercury is not doing that. Mercury tends to go around something else, not necessarily Earth. But people was more or less convinced that Earth was center, so they tried to bring additional orbits to the fundamental orbit they already have, and that is what we now refers to
So
as
that means
epicycle.
to fit everything to our belief, we made
Yes, yeah,
so many nasty things.
amendments in our own understanding or our own belief of this kind of
So
picture.
when I hear this story, what it tells me, when the moral of a story, what I get is actually for every phenomenon there will be a simple explanation. Um,
But yeah, that is a point that I wanted to make for a very long time. If you trace back in history and we want to fix where the geocentric model started, it was probably 2000 years ago. We have to go back as Ptolemy or Aristotle if you want. So that is more or less 2000 years ago. But then came in your class you are probably going to learn this in 1 hour,
Yeah, really.
or maybe 30 minutes lecture is more than enough, or maybe this conversation, however long this is going to be. um, that was 2000 years ago, and then we came to Nicholas Copernicus,
Mm.
and that time period is roughly 1500 years.
Mm.
Okay, you can just Google Copernicus and Ptolemy and find out their birthdays and calculate the difference. I don't remember these numbers offhand, but the thing is that is roughly 1000 years or 1400 years.
Mm.
So it took more than a millennia for people to understand and accept this. Okay, so it is not easy. Tracking Mercury is very difficult. Look up in the sky, and do you see Mercury?
Yeah.
I don't. So
Even
it's
in the
very
night sky, we can't find Mercury.
Yeah, it is
Unless
very
we have
difficult.
something, other
Yeah.
apps.
Yeah, unless we are dedicated, unless we are, unless we find ourselves in a purpose to do that, we will not do that.
Yeah.
Okay, it is very difficult to even understand the solstices unless we are giving careful observation. So, as you said, careful observations are part of it, but that takes time. Okay, it can't be just in a snap of a second or so. So, from the geocentric model to the heliocentric model, it was not an easy transition because, okay, our belief system or our understanding suggests that these things are moving in circular orbit, whatever that belief system was. People have to stick on to that belief system and make amendments so that they are not too far away from the truth. That is what most of the time people think. So they change the perfect circle with additional epicycles, but one epicycle was not enough. Okay, people started observing Jupiter, for example, and it was going faster and slower and then going faster, but it is not going around the sun. There was no idea like that at that point. So we have to bring more epicycles into the picture.
And these planets have
There are satellites,
yeah.
and satellites are going around these planets.
The
But
epic cycle system will be more and more complicated if.
yes, so that is when we should realize that we are doing something wrong. Epicycles over epicycles, and I think that term is now part of the science literature to indicate bad science. Like, yeah, there is. Let us.
I mean, there is something called in philosophy, something called Occam's razor.
I'm very bad philosopher. So
No, I'm not good in philosophy, but I heard this. Occam's razor is something that if we have a conclusion from some premise, or any assumptions, if the assumptions are few, that means that is likely to be true. One with few assumptions could be likely to be true. Same to be like similar to this, like with a simple explanation means it could be more true.
yeah,
Okay, back to
I understand your point.
Yeah.
I don't know the technical, official, philosophical term for that, but that is exactly how people think. It should be too simple to understand. If it is too complicated, either we are doing something wrong, or maybe something
missing.
big missing from our picture. So the epicycle was an indication of suggesting to the world or announcing to the world that we are doing something wrong. So all of this changed with one single paradigm shift. Just remove Earth from the center and put Sun there. And if Sun
That was so
is
simple.
the center and everything goes around the Sun, then all the epicycles just disappears. We do not need an epicycle at all. And we could precisely explain everything's motion. Okay, we are not predicting anything. We don't have a kinematics yet. We are simply saying that
We are
that
just observing
explains-
and creating a model.
yeah, and we are not making calculations at that point. Maybe we are doing some rough calculations, or maybe there are some calculation people can come up with. But I wouldn't say that is an equation like Newtonian mechanics. Newton is still not in the picture.
Yeah.
So we started with geocentric, then we ended up having epicycles, but a paradigm shift from Earth-centered to Sun-centered universe changed all this epicycles.
And most of the people at the time couldn't accept this change.
Yes, even people were burned alive at that point because it was against the teaching of several
Religion.
institutions. We should not be referring their names because of political reasons, but whatever that may be, people were burned alive at that point. You know, that was kind of a criminal activity to proclaim to the world that Earth is not the center.
And
Because
actually,
that just destroys the whole narrative they have. You know, Earth being the center and it was being created. So if that is not the way the universe is, then if we are just mere a planet going around the sun, that destroys our significance. And when our significance is gone, everyone else's significance automatically falls down like a dominoes. So people don't want that.
at this point, I want to make a comment that if we are asserting we, but and we done this and we discovered this, there is a problem because only few percentage of the total population of the Earth we live contributed to this. Most of them were aware or against it, but we call it we to make something like we are the humanity. We found everything.
Yeah, I would say that we as a human being, maybe I need to be politically corrected now and then, but
I know I'm not digging into that, but I said there is something very interesting about we.
yeah.
Okay, back to the point.
Back to the point. So we started with geocentric, and now we are at the heliocentric model of the universe. Again, we are not talking about the solar system, although we refer heliocentric, not geocentric. Heliocentric model is very closely related to our solar system model, but we are not modeling the solar system at that point. I should say we were not modeling solar system at that point. We were trying to understand
how it works,
how the whole universe is. Okay, so there is a slight difference there. So
up to then, up to now, like universe is only this 9 planet, not even 9. This planetary system.
Yeah, planetary system, whatever we know. At least we know about Jupiter and Saturn for sure. And we know about Mars, definitely. And we know about Mercury and probably Venus. So, and moon is there. But if it was just moon, earth and sun, there was nothing wrong with keeping earth at the center. Because whenever you do a binary system, everything goes around everything else.
Yeah.
So whether it is, if you are taking earth and sun, is it the sun going around the earth, or is just earth going around?
Three are in same plane, I can say.
Yeah.
Almost same plane.
So keeping earth at the center wouldn't do much harm, although the technical accuracies might be different because sun is much bigger, and you know, the center of that system is within the sun. So technically I'm being very naive and less
for
accurate.
most of the purpose it's fine,
at least for the purpose of earth and moon. It does work. So the point is, it took an enormous amount of time, it took an enormous amount of observation to verify this and accept this as. But that was not the end of it, because if you make very detailed observation, you will realize that circles are not good enough to explain these orbits. But we are very reluctant to throw away circles. So can you guess what we did at that time?
If you change the shape of circle a little bit, you will get ellipse.
But even before going to ellipse, because that would be a major step, they decided, okay, sun may not be at the center, it might be slightly eccentric. Okay, the planets are going around the sun in circular orbits. That is still the case, but sun doesn't need to be at the center. That was the assumption.
We still stick on to the idea of
circular orbits at the time. So people stick on to the circular orbit, but they decided to slightly amend the demand that sun is at the center. Sun might be, because we already lost the place, right? We were at the center of the universe. Now we are not. Now we don't care whether if there is anything at the center at all. So sun doesn't need to be at the center. It's slightly eccentric. So that is another picture. So it started with the simple geocentric, then to heliocentric. In the heliocentric itself, people were able to create this circular orbit and make slight amendments to the center. Then what happened is very, very difficult to explain, because even if you want to understand whether from that heliocentric model to the current model of the universe, we need to go beyond the solar system. That is the problem, because first of all we need to identify that sun is just a star like every other stars in this universe. That is quite difficult. Like, how do we say that there are stars and every other star is similar to sun, at least to a certain level, and there are planets going around those stars? We can't make that guess, or we can't make that accurate prediction or observation yet at that time. So it is not easy or very simple to go from the heliocentric model to the current universe. But there was an in-between time where people tried to model this more rigorously. And I think that is where people like Galileo or Newton came into the picture. And before these people, there is Tycho Brahe and Kepler, Johannes Kepler.
We should not forget them.
Yeah, we should not forget them. So they have done enormous amount of observation, especially Tycho Brahe. Can you guess why people were doing such detailed observations?
I mean, maybe because of timekeeping or trade routes.
Trade routes, exactly. So the
serving the king.
Yeah, serving the crown. So the crown or the royals, they tend to fund these people because they wanted to expand their kingdom, and they have to go beyond the seas or deserted land, and they have no notion of directions. When they are lost in sea, they can't keep up the
So
directions.
somehow they could they believed or they trusted the sky can be the route.
Yeah, sky can be a very good map of directions, because the patterns repeat, and as you said in the beginning, there are patterns that stays the same, like the constellations, and it is a very good timekeeping system. So creating a timekeeping clock is very difficult. Synchronization of clock is very, very difficult, even at the current moment. Back then it would be even more difficult. Like, for example, some people started out from London and reached somewhere else. They don't know what time it is, because time zone have shifted. I don't know whether clocks and watches were invented at that point, but let's say it is. But synchronizing two clocks, because clocks works on the basis of simple pendulums. Okay, at least simple pendulum is kind of a clock. At least we can keep time with that. But when you transfer the simple pendulum, which is created here, which is synchronized right now, and if you transfer that one to a ship, which is off to go, I don't know whether it is very simple to explain, but the synchronization might be lost, and it might be showing some other time. So synchronizing two clocks is very difficult. Even now with atomic clock precision, it is very difficult.
For at that time, it's very simple to look at the sky, because it's always synchronized to everyone.
Yeah, at least people could get the notion of directions and things like that. So people were funded. I think that is a very good technical term to bring at the current
nowadays
economy.
kingdoms will fund this kind of astronomers.
Whether we should be funding fundamental science, we need this fund. Okay, that is what we do for a living. People were very well funded. The astronomers were very well funded during those time to get very accurate map of the sky, because that helps them navigate through the seas and probably deserts if there are, because as you said in the beginning, these patterns pretty much says the same. So if you look at some stars, we don't know whether they are stars yet, but at least these bright objects, they tend to stay in those positions. And since they stay the same, that's a very good reference. With the heliocentric picture, or the picture of the universe in our hand, what we tend to have is, the sun is at the center, everything goes around the sun, and then there are satellites that goes around the planet, but the stars are pretty much the fixed. So they are fixed in something called as the, celestial sphere. So celestial sphere how large is that sphere, because when we say or talk about sphere, we tend to talk about the radius. But we can't just put a number to that. It is something very far away from us, such that it all appears to be in a shell. Okay, so we can put a coordinate system into that, and we will have longitude and latitudes in the picture.
Maybe we can have a. We don't have a radius, but we can have some kind of.
Yeah, longitude and latitudes.
Yeah.
That is how we coordinate these things. So we have this very big celestial sphere, and things are moving in the celestial sphere, but the celestial sphere itself appears to be fixed. And what I refer to the celestial sphere is these stars or whatever these bright objects.
Projection of the entire universe that we see from our Earth.
So it simply is like a very large sphere, and Sun is also tracing a very particular path in this sphere, which we now call the zodiac belt. And this zodiac belt has 12 constellations. You know, if you want 100 constellations, you can still make that. But the thing is that for the purpose being, 12 was enough. So we have 12 zodiac signs and that appears in the zodiac belt, and altogether we have 88 constellations. So constellation is trying to make a map or regionalized divisions in this celestial sphere. It is easy to identify because we are pattern recognizers in a sense. We recognize patterns rather than numbers, at least to me. So they divide the entire sky into 88 constellations, if I am not wrong. Maybe you have to cross check that number. But out of this 88 constellation, 12 is where the Sun is going, and that is what we call the zodiac belt. That is the whole picture. We don't know whether these stars are moving away from us. We don't know whether these stars are kept as such or part of a different system. We also see a very bright milky thing going around the sky. We don't know what that is. So those were the observation till that point, I should assume. I don't know whether that is 100% accurate, but nevertheless that is naively correct. And the next big step perhaps towards the modern physics was by Kepler. Yeah, Kepler, in the sense that, you know, we have enormous amount of data, but can we make a correlation, a numerical correlation or an empirical correlation between these quantities? That is a very big question. And Kepler traced out, you know, he has almost 200 years of data. He's not 200 years old, but he has this enormous amount of data, which he took from Tycho Brahe. I don't know whether he stole from Tycho Brahe, but that is for, you know, controversial discussions. But other than that, Kepler did a very rigorous data analysis.
Without calculus, without computers.
Without calculus, without computer. Maybe at that time they had their own way of computing the things. Maybe some mechanical things were there, I don't know.
Maybe logarithm and tables and all.
Yeah, they might have something, but definitely not calculus. So without these things, he tried to map the orbits of these planets and came to a realization that the period of the orbit and the distance has a relation, a non-linear relation.
Maybe that's something called creativity. Without even any tools at that time, he found something wonderful from the data.
Yes.
That is purely not obvious from the data.
Yes. Simply put, it sounds very easy, but there is a very big challenge to that. We could probably find out the period of the orbit because we just have to observe this and find out how periodic it is. You know, maybe 10 years or 5 years of data would be enough to do that. But the biggest problem is the distance. Like, how do you estimate such large distances? It's very difficult, even at that time of Kepler, I would say. Like, what is the distance of moon from the earth? Tell me.
Now it is easy, but...
Now it is easy. Tell me the number. Maybe a rough number.
How I remember the distance between earth and the moon is, I told that it takes light to 1 second to reach surface of the earth to the surface of the moon.
So it is roughly 3 lakhs kilometers. So that is exactly how we are taught. It is taught in such a way that you remember the thing.
Yeah.
And in order for you to remember, you should also remember the speed of light. So it is not discovery, it is not realization.
Nothing.
It is
Just a
simply
memorization.
memorizing the fact.
Really.
That is exactly what is wrong with our education system. But let us not go in that direction. But measuring the distance is an enormous challenge. For example, if I am standing here and there is a coconut tree over there, I need to find out how far it is. Maybe I have a notion, okay, it's just few steps away. But how much metric distance is there? Like if I want to make the calculations or the observation in meters or kilometers, I would say probably 10 meters, 20 meters, because I am experienced with that number. I know what a meter is, I know what a kilometer looks like. But how do you measure something that far away? You know, how big is sun? That is another question. From here, it is, I can cover the entire sun with my palm, or maybe my thumb is more than enough. So there is moon, and moon and sun, maybe I should say luckily, they have similar or very close angular size in the sky. They cover the same area in the sky. That is why when there is a perfect solar eclipse, it pitch back. So yeah, even with that into our understanding, it is very difficult to estimate that number. And that is where trigonometry coming to the picture. Maybe not the trigonometry that we learn, like sine, cosine, tangent, all these technical terms are very difficult to understand. When we were taught, I think probably high school, right?
First we taught is the table. You had to remember.
Yeah, it's all start with the right angle triangle, and then there is hypotenuse, adjacent sides, opposite sides, all these. You know, it has to be less than 90 degree for some reason. So trigonometry began as this table keeping to find out the distance. Even before that, how did people realize that Earth is spherical? And people have measured the diameter of or the radius of the Earth. So trigonometry has done its part. Maybe it wasn't an official, series expansion that we know right now, because sine of x can be expanded into a series of x. Maybe people didn't knew that at that time, but at least they kept these ratios in their mind.
What they were doing was maybe comparing triangles,
Exactly.
comparing ratios.
Exactly. So let us assume this is sun and here is the moon, and this is moon has an angular diameter. It has a diameter. So when we look into the sky, it makes a triangle, and the sun also makes a triangle down Earth. So if we can fix the distance in the ground and estimate one of this length, we could actually measure the whole system. But there is a slight problem.
We don't know any length.
We do know the length in the ground, but the measurements need to be enormously accurate. And what are we measuring? We are measuring angles. It's very difficult to measure angles. At least even with the current technology, we still use this angle measurement, the parallax method, to observe distant object. But what is this angle? Like if you are making this observation with moon, the horizon or somewhere, and phases of moon gave us an idea where the sun is, the light and the reflection, everything. So we need to make this angle very, we need to measure these angles very, very accurately. And it is almost like a fraction of a degree. Like for example, in our high school, we used to get questions, draw a triangle, measure the angles, and prove that it is 180 degree for a Euclidean triangle. And when we do that, it is either 179 or 181, because we make rough mistakes in our angle measurements. Although technically it will be equal to 180, but when we do the measurement, there is 180 plus or minus something. This plus or minus is where the whole science is. I would say that is the only thing about science that we need to remember, because scientists always put an error bar to the calculations.
Without error bar, there is no meaning in the measurement.
Yeah, exactly. So this measurement of angle measurement is very difficult, and I don't know whether I will be able to do that measurement ever in my life, unless I am given the sophisticated instruments right now. But It was done during the time of Tycho Brahe and Johannes Kepler. And they, not just them, the entire team of astronomers made these observations, and that is what enabled Kepler to finally, not necessarily fix the length, but at least come up with an empirical relation between whatever lengths they knew at that time with the time period. So that is an enormous transformation people had. And or the society, or the scientific society, even if you say that is a very few percentage of the entire population, that is how it all began. But even funnier part is when Newton and people like Galileo came into the picture. And they realized that, or somehow, maybe I should pinpoint to Newton, the motion that we experience here on Earth, if you throw a ball, it is having a particular kind of trajectory. If you drop a ball, or if you throw a ball up, whatever you do, it tends to have a trajectory. And you can use the same mechanics that you use to explain the motion of a ball to explain the motion of these heavenly objects such as moon or sun. So that is when we derive Kepler's law from Newtonian mechanics. At least that is a graduate level problem these days, at least. Not graduate level technically, maybe an undergraduate level.
But we used to do
examples.
But we used to do in graduate level.
Yeah, maybe graduate has a very general term in the global sense. But nevertheless, after high school we do that calculation. Maybe immediately after the high school we do that calculation if you are studying physics. So the thing is, we can derive this empirical relation from something fundamental. I think that is where I should put a mark on the beginning of the modern physics. The invention of calculus, everything came into the picture. So, yeah, I think that is a very nice place to stop in a sense, because from these tedious observations, we now have a framework, a mathematical relation between these variables to predict few things. Okay, that predictability is so powerful, even people misuse it. In fact, I just want to point out that people always tend to, blame astrology in the sense that it is nonsense or it is not scientific. The thing is that I have heard this story, like if I am able to predict the future of the heavenly sun, I should probably able to predict your future as well.
That's the basic logic behind it.
Yeah, that is the logic behind astrology applied to human life.
When we look at that sun, as you told, like sun can be like we can put our thumb and
make the eclipse.
Make the sun disappear from our vision. See, the sun is very small to us, and that sun itself lit the whole planet. So that's very wonderful for them. Like it is small object moving around periodically and lighting up the whole earth. And in that object itself can be blocked by another object, and that can be predicted for a guy. So he's a superhero at that time.
Yeah. So because the sun, moon, everything else was considered godly at that moment, and if someone can predict the fate of God, they should also be able to predict the fate of human beings. And that is where something nonsense came into the picture. So if you're just trying to map out all these periodic events, it is simply just observation, simply calculation, simply prediction. That is good science. It is when we use these jargons into places that it should not be used, that is when things go out of our control and make a fuss. So in a sense,
so the evil lies in the interpretation.
Yeah, devil lies in the details. So it is not just interpretation, it's about how we use it and understand it.
Yeah, I mean, we have the data, we know how to predict different things, and if we have a wrong interpretation,
Yes.
then that is a bad thing.
Yeah. Wrong interpretation, completely wrong, in a sense that that is not exactly what the scientist intended to make.
Yeah.
Like for example, let us come back to this current century and look at picture right now. Right now we are in a phase we assume that the universe is expanding and undergoing an accelerated expansion. And when we say accelerated expansion, it is a very, very rigorous observation. It can't be done in a single day, or maybe 10 years is not enough to make that conclusion probably. But the thing is, we should not assume that it is as it is. We, when we are reporting a number, we always come up with an error bar. And that error bar is enormously important, because a slight change in that would completely change our understanding of the universe. It will change our perspective. It will change the very question you started with, whether it all started with the Big Bang. Because technically, when scientists talk about something, it is very, 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 very rigorous. I'm not saying it is very difficult for commoners to understand, but it is not too simple to understand, because when you make things too simple, you lose the essence of it.
I heard somewhere that you can make it simple, but not simpler.
Yeah, you should not do that. For example, the standard model of particle physics, Higgs gives mass to everything, right? That is the God's particle. Higgs is responsible for the mass of electrons, whatever things that you can come up with. But Higgs cannot be the reason behind the mass of neutrinos. If it is very difficult to understand neutrinos. Because that is how the entire standard model is. In the standard model, neutrinos don't have mass, but neutrinos oscillates.
So thing is, it's not simple that
Yeah.
Higgs is responsible for the whole mass.
Yeah, when people say Higgs is responsible for the mass of electron, they mean very specifically
Fermions.
not fermions, like neutrino is also
Yeah,
a fermion.
sorry.
So they mean the things very, very specifically. Under these circumstances, under these conditions, under this data, this is what it looks like. That is exactly what scientists have been doing for the past 2000 years or so. So in a sense, when Kepler discovered these relations between the distance and time period, that was an enormous jump from, at least now we have an empirical relation about how these things are. If you know the distance, you can predict the period, or if you know the period, you can predict the distance. But the proportionality constant was not fixed. That proportionality constant has to come up with Newton's mechanics, and the distance measurement, everything has to be there. So other than that, everything came very coherently for people like Galileo and Newton to come up with such a beautiful theory, which is right now we call a theory of gravity, which explains why everything falls down. Like my sister used to mock at me because I'm doing physics and she's doing medicine. Like, are you sure Newton discovered gravity when an apple hit on his head?
That's a popular story.
Yeah, that is a popular story. And she was asking, like, has Newton never dropped anything? Like, if you drop a knife, that is also equally important as an apple falling, right? So, and then there was things like, if you light a candle, the flame is going up, the smoke is going up. So everything is not falling down, some things are going up. Birds are flying around, clouds is up there, it is not falling, but the snow falls or rain falls. So people have to understand fluid dynamics a bit, at least a sense of pressure, at least a sense of, viscosity or gravity, in a sense that people understand right now. So it is not easy for Newton himself to do that. And perhaps Newton is the greatest mind of all, because he didn't had a theory to work on. He didn't had the mathematics to begin with. He created the mathematics he wanted. He created a theory, and he did enormous amount of calculations. there is a story about Newton. Like, there was one problem. I don't remember the problem itself. So it was an open problem. No one can predict something. I think it was the Barrett's problem. Oh, I don't know.
Yeah.
Yeah,
Shortest distance.
yeah, shortest distance between 2 points if it is held like that. Let us forget about the problem. That was a problem at that time, and people were, inviting other legendary mathematician and physicists at that time to solve this. And one, I think, there was this king who announced the problem, or maybe some royalty, and they received enormous number of, results, but only one was right, and there was no initials at the end. Like, for example, if you submit an assignment, you write the name, yeah, submitted by Adithya, submitted by Manosh, submitted by someone. But Newton didn't write his name, but it was too obvious for everyone.
If this work should be
If
done,
this work is correct, it
then
has to be from Newton. Like, no one else is able to do this. I don't know whether this is a true story or not, but probably it is true.
it tells Newton was so famous at that time.
Yes, Newton was so famous. He did all of that, and then he turned 25 or 26. He was so young when he discovered these things. He has time. He is enormously rich as well. So political situations are slightly different. But nevertheless, he did an enormous amount of work in developing this theory. So if you read Principia, I haven't done that. It's very rigorous and very meticulously crafted. There is no loopholes in Principia, at least not. Maybe relativistic correction has to be done right now, but nevertheless, at that point, with that framework, that is the best thing people can come up with. At least that is what I think. Even our professors tends to say that Newton's Principia is worth of 25 PhD thesis. That is how much gravitating that was. Even the society was accepting this book, because back in those days, printing was expensive. It's still expensive, but at that time printing was expensive, and Principia was copied, I don't know, a few thousand times at that time, and people were ready to buy that book. At least for the libraries, like some librarian used to order hundreds of those books, because libraries were very well established in Europe. So all these things coherently aligned in a way that Newton was able to come up with a theory of gravity, which then predicts almost everything that we see today. Okay, even right now we know that Newton's gravity might be slightly wrong, or maybe an approximation because of Einstein, but the work that Newton did is miraculous, because using Newtonian mechanics, we were able to identify an additional planet.
Yeah.
Right. When I was in high school, or probably when I was in school itself, we were taught there were 9 planets, starting from Mercury all the way up to Pluto. So there is Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune and Pluto. But there is a problem with Uranus. It was not following Newtonian mechanics. There is some slight change in its orbit. So either Newtonian mechanics is wrong, or there is another planet out there that is perturbing this orbit. And if there is another planet and it is giving this much amount of perturbation to that orbit, and Uranus is right here, then the other planet has to be here at very pinpoint location. People were able to predict that location
Using Newton's
Newtonian mechanics. And then they looked at that position and they discovered that planet. So that is how powerful Newtonian mechanics is. I get goosebumps when I say this.
Yeah, really.
So the strength and the rigor that went into it, there is no easy way to falsify it. There is no easy way at all. And
We will get more confidence if you
yeah,
in the confidence in the theory will.
yeah, the confidence in that theory, the people started accepting that theory all around the world. I don't know how much around the world, but nevertheless, people who are doing modern science or astronomy, or I don't know, cosmology was not even a thing at that time, but people accepted it to the very core. Then again Mercury came into the picture, and Mercury's perihelion precession, everything gave a different prediction from Newtonian mechanics, and people predicted, okay, there might be another planet there, or there might be something else going on.
Maybe dark planet.
Maybe dark planet. People used to call them planet Vulcan,
Yeah.
from the Star Trek or Star Wars. Don't hate me for saying the wrong name, but nevertheless, people used to, maybe there is a dark planet out there. Maybe we are not seeing something behind the sun because we have never gone beyond the sun, on the other side. Earth goes around, but what if there is something that is exactly at the opposite part of the earth? We will never be able to see that. So maybe there is another planet within the limits of Mercury. People started predicting its orbit, people started predicting its position. Nothing. Then Einstein came into the picture and proposed the general theory of relativity. There is a whole story we are missing right now. But even then, even when Einstein is right, I still think Newton has done a greater job.
Yeah, really.
Because it is not the position of the difference that we are getting is 43 or roughly 43 arc seconds per 100 years. That is a shift that is been shown in Mercury's orbit or Mercury's precession of the orbit. So it's a very minute detail. See, the angle measurements are still coming back to us. So it is 43 arc second. Can you show me 43 arc second? It's very difficult. So 1 degree is 60 minutes and 1 minute is 60 seconds. So 1 degree is, I don't know how much 1 degree is. This much? Oh no, it is too much. So this is just 1 degree and 1/60 of that is 1 second, and 43 arc second. That means you divide that second into 60 pieces and you just take 43 out of it. That is a difference. And that difference is not coming in 1 day or 2 days. It is coming with a time lapse of 100 years. 43 arc seconds per century. So Newtonian mechanics was able to predict the orbit, was able to predict the precession very accurately, but not as accurately as we were observing, because we had very good astronomers doing very, very accurate calculations. So Einstein theory was able to account for this mismatch. And that is where Einstein's fame came into the picture, with Eddington's observation of the eclipse and shift in the position of starlight. All these things gave fame to the Einstein, but Newton was able to predict things properly. So Newton did an enormous amount of work in order to establish his theory, and it works pretty beautifully, if you want to ask me. The correction required is just 43 arc second in a century, which means it's a correction on the first place, which also means that Newton was able to predict the precession of Mercury's orbit based on every other gravitational interaction, like there are other planets in between. Not in between, there are other planets around. So what Einstein did is an entirely different paradigm shift. In order to understand Einstein's general theory of relativity, one must also understand special theory of relativity. And in order to understand special theory of relativity, one must also understand electrodynamics to a certain extent. And that is how physics has evolved, like feeding each other and all. And in order to do real science, if you want to do real actual science, that is exactly what you need. You need to go through the mindset of these people. But they are divided in time. It's in the past. We can't just go and talk to them. But the better thing that we can do is actually read their work. For instance, we all learned about atomic models, starting from plum pudding model or Dalton's model of indivisible atom. Then the first thing is that we learn about plum pudding model. There is a positively charged sphere and electrons embedded in it. End of story. Is that what?
It seems very simple.
It's very simple. It's very simple and it's very trivial to a certain sense.
So when I was studying, when I heard plum pudding model, I thought like when I was in that place, I could also guess this theory.
It feels like almost like a 5-year-old kid came up with that idea. But if you go and read J.J. Thomson's actual paper, at that time there was electrodynamics, I believe, and the paper is too rigorous to understand. although it is completely wrong. We now know that atomic model is not plummeting model. We have better models right now. But at that time, with the theory that they have, they came up with something better they could. And that is what it is. But when we water down this whole theory to something as pudding, that is throwing away the enormous amount of works J.J. Thomson put into this whole circus. And I believe he also received a Nobel Prize, correct me if I'm wrong. It wasn't given to someone who just discovered one equation or one simple model. For example, if you look Einstein's Nobel Prize, he received Nobel Prize for photoelectric effect. And it feels like almost trivial to us, like kinetic energy and
just simple equation.
yeah, it's very simple equation that
Energy
we need.
conservation equation. We can could also guess if we are in the position. We can think like that, but it's actually not really. It's not obvious to.
Yeah, we learned that in higher secondary, I believe, and it almost feels like I could also come up with that equation. If I were to invent a time machine, I could go back to 1900 and write down photoelectric effect. But still, that wouldn't be same as Einstein's paper because he has done so many work in it, and people are so adamantly confirmed about the fact that the light is a wave to tell that light is a particle. Planck did something. He assumed that light's energy is quantized, but that is different from saying that light is particles. So in order to confirm that, it takes a different level of intellect, a different level of creativity, a different level of what I can say. I don't know what word should I say about it.
Because it's changing the whole perspective.
Yeah, it's changing
the once established perspective.
Yeah, it is also challenging the existing perspective as well. Because Millikan, who proved photoelectric effect to the very end, he also received the Nobel Prize for verifying photoelectric effect. His intent was to prove Einstein wrong. He wanted to prove Einstein is wrong, but he did the experiment as a very genuine and honest person, and instead of proving Einstein wrong, he proved him right. So that is exactly what science is to be. Rather than proving one right or wrong, it is doing with honesty. That is where it is important to read original works, although it might be difficult to access, it might be difficult to comprehend, it might be difficult to understand each and every word written in each and every paper. But people should read it and should realize that people they were also as confused as we are. For example, we naturally tend to assume black hole has a temperature, Hawking temperature, whatever jargons we can pull up. But if you go and read their original paper, they were really confused about using these terminologies because that is how science is done. So if you want to do science, you must read these papers rather than popular science videos or books. Even this conversation is not going to create real science. It's just a historic narrative of what actually happened, and the history tends to be more complex than it is.
So my takeaway is we all have preconceived notions about anything, anything we all have preconceived notions. So science is actually in studying a subject apart from our preconceived notions, and what the result says, we have to accept it.
Yes.
Even if it is our favorite belief,
Yes.
even if it is our dearest concept,
Yes.
we have to change, we have to move on.
Yeah.
That is a way of thinking, and that is a science.
Exactly. And so if you go back to your first question, what is Big Bang? Is it simple to answer? No, it is not. Is it simple to understand? No, it is not. But is it simple to convey in a popular level? Yes, it is. But when we convey things in popular level, we over dilute things, which is a very bad thing when it comes to science. Yes, we can talk about strings being vibrating strings and electron being
Maybe we
a
can
string.
pull students into it.
It can attract people into the subject, but once people start doing it, they will not feel that kind of attraction. They should be motivated by a different kind of attraction, and that is different. And that, I believe, it's a entirely different topic to discuss, which may be something that we can do later on. But in this very nice environment, I think it's a very good point to stop. Okay.